Right. Ready to go when you are, guys.
Yes, you can start now.
Okay. Oh, we lose Braden. No, there he is.
Hey, welcome to Team Chat Atlantic, and we present the A55 Vulture. Our group consists of Sam Beck, Michael Coletta, Jane Cosme, Tristan Kroger, James Monahan, Braden Sabo, me, and Daniel Singer. Slide. So I will be presenting our airfoil selection and our wing geometry design. So when considering what airfoil to use, there's 1,000 options that we can choose from. So to expedite this selection process, we first needed to study our design mission and then make a few assumptions regarding it. Given the light attack aircraft design requirement, it is necessary for our aircraft to be subsonic, which means the Mach will be somewhere between 0.2 and 0.6. This range then leads to a Reynolds number between 1 and 10 million. And it is important to note that this selection process had all its calculations performed at the aerodynamic center of the airfoil, and that all these calculations would be strictly two-dimensional, and calculations later in this report will be three-dimensional. So now with the assumptions laid out, we can move to the physicalities of the airfoil. Camber selection would be the first and most important design selection, as it will directly impact our design mission. A larger camber will result in more lift at a given angle of attack, and this will directly help to achieve the required takeoff and landing distances from the design mission. Slide. So the next airfoil characteristics I'll go over is the thickness ratio. This is strictly determined off of historical data of other aircrafts in its class. So based off of our 0.2 to 0.6 Mach number range, this would put our thickness ratio at 0.15. With this thickness ratio and our chosen airfoil route, which is the NACA 638-415, we can estimate the maximum lift coefficient to be 1.5. Determining the thickness ratio is essential as it directly impacts the lift, drag, and stall characteristics for the aircraft, and the weight. Slide. With these two characteristics determined, we can then narrow the selection down further. We immediately chose to eliminate the 4 series NACA airfoils because of its usage in the mid-20th century. The 7 and 8 series were removed because its lack of historical data and its experimental usage. The 16 series was removed because it does not focus on wings. The 5 series was removed because recorded historical values for drag and weight were too large. They also have very poor stall behavior. This narrowed down our selection to both the 4 and 6 series, which can be seen on a drag polar curve showing coefficient of lift versus drag coefficient on the next slide. Yeah. The curves of this graph are determined from airflow separation, not drag due to lift. Analyzing wing loading for the takeoff and landing design mission requirements, we could find our target velocity and coefficient of lift, and target coefficient of lift, which were 200 miles per hour and 0.748 respectively. This allowed us to narrow our selection to the NACA 638-415, and this is our route cross section. Slide. With regards to wing geometry, the necessary characteristics to determine were aspect ratio, wing sweep, taper ratio, geometric twist, and incidence angle. The aspect ratio was determined to be 2.77, and this was based off of historical data. This low aspect ratio provides structural advantages specifically for storage applications. Our wing sweep angle was selected at 5 degrees. This was determined by the commonality of light aircraft to have small wing sweeps, if any wing sweep at all. The benefits of wing sweep would be high speed lateral stability, and it also helps to improve low speed responses. The taper ratio was determined to be 0.2, and this is based off the quarter chord sweep in combination with historical data of other aircraft in its class. Slide. Geometric twist was chosen to be 0 for several reasons: manufacturing expenses, material constraints, and error propagation. Incidence angle was also determined to be 0 based off historical data of drag optimization for attack aircraft. It is essentially negligible, so incidence angle is not required. We selected the root of the wing location to lie flush with the bottom of the fuselage, and this is for maneuverability applications. Slide. A wing dihedral of 4 degrees was selected, and again, this is from historical data of aircraft in its class. And the dihedral plays a big role in lateral stability, which will be covered later in this report. We chose to have no high lift devices as the maximum lift coefficient was close enough to the max lift coefficient for our airfoil, so we were able to deem them unnecessary. All of our aerodynamic characteristics of the wing were found using Xfoil, and this is a program used to run analysis of subsonic airfoils. Testing for the airfoil was done at varying angles of attack, Reynolds number, and Mach numbers. These results can be seen in the accompanied graphs. Slide. So we have our drag versus angle of attack, coefficient of drag versus our angle of attack here. And like the next 2 graphs we're going to see, the important takeaway for them would be that with the varying Reynolds numbers, the trends were almost identical. And this, again, is the same for the next 2, which is coefficient of lift. Slide. And okay, we skipped lift, but okay, and this is our coefficient of lift. And as you can see with the varying radial numbers, the trend is pretty much almost identical. Slide, and you can see the same thing for the coefficient of momentum. It's good. Slide.
So my name is Michael Coletta, and I'll be talking to you about the propulsion system that we chose. So the engine is very important in determining the capabilities, limitations, and the design of our overall aircraft. Some of the important parameters that we had to consider were fuel consumption, weight, and thrust. Some of the main type of engines that we considered can be seen here to the right, and they include the turboprop, the turbofan, the turbojet, and the piston prop engines. Slide. There were some early eliminations of a few engine types, and those can be seen here. First off was the piston prop engine. This was chosen to be eliminated because of its low performance and its very low max speeds. It also was unable to reach the high altitudes that we needed for our missions, and there was not enough power generation for our payload missions. The turbojet engine was also eliminated for its too high performance. We did not need to travel at such high speeds or generate as much power as the turbojet can generate, and it was essentially considered overkill for the missions that we had at hand. In addition, it is also a lot less fuel efficient and needs a greater runway distance in order to be utilized. Slide. That leaves us with the remaining considerations of the turbofan and the turboprop engines. They are both variations of the turbojet engine and aim to be more efficient at lower speeds. They do this by moving larger amounts of air across a larger amount of area of the engine. The turboprop does this using a propeller, and the turbofan does this using multiple fan stages. Both can be seen below. Slide. The bypass ratio was one of the first important considerations that we had to take into account. The bypass ratio is the ratio of the mass flow rate of the air coming into the engine and the mass flow rate of the air going out of the engine. Turboprop engines generally have a higher bypass ratio ranging from 20 to 100. This high ratio, however, reduces the max flight speed due to the shockwave formation that is formed by the propellers. The turbofan is generally much lower, and it ranges from 0.2 to 5. Slide. The fuel consumption comparison was also done between the 2 engines. The turboprop engine performs a lot better at lower altitudes, and this is due to the fact that the reduced air density is a hindrance at higher altitudes for the turboprop engine, and its efficiency is a function of the propeller diameter. A turbofan engine, however, performs better at higher altitudes, and this is because the increased air drag on the airframe occurs at lower altitudes. Its efficiency is a function of the internal compressor limits, such as temperature. Slide. Takeoff and landing distance was also taken into account. For the turboprop engine, it can land on shorter runways and generally need about 3,000 feet. It can also land on a lot rougher terrain like dirt or grass, which would be used in our missions. The turbofan engine, however, needs a lot longer of a runway and generally needs concrete or more solid ground to take off and land from. Slide. The final selection tables can be seen below, and some trade studies were conducted. As it can be seen, the turboprop engine shows advantages in dry weight as well as bypass ratio in the first chart, and suitable power was found for the turboprop engines over the turbofan engines seen in the second chart. Slide. For this reason, we chose the turboprop engine over the turbofan because it had many advantages in many of the key parameters. The final selection of our engine was the Pratt & Whitney Canada PT6A68B turboprop engine, which can be seen here below. Slide. Now, the reason for the turboprop selection of the turbofan was advantages in many key parameters, such as flight ceiling, payload, flight endurance, range, takeoff and landing conditions as well. And the selection of this model over some of the other turboprop selections were advantages in dry weight, bypass ratio, as well as power generation. Slide. So the propeller design was a pretty important parameter to decide when we were designing our power plant. It must be designed to achieve the desired helical and static tip speed, which for our design was 290 and 252 meters per second, respectively. And those equations that we used to get those values can be seen below. These tip speeds give us a general diameter of about 8 feet for our propeller. Slide. The number of blades is also an important thing to consider in that they cannot be too high or too low. Too few blades produce large pressure pulses and increase vibrations and cabin noise to the cockpit, which is unwanted. Too many compromise on efficiency. For this reason, we chose to go with three blades, which is a happy medium. Slide. The thrust calculations that were done for our engine can be seen here. The forward flight thrust as well as the static flight thrust are both acceptable for our mission requirements, and their corresponding equations can also be seen here. Slide. The exhaust design also had to be considered when designing our aircraft, and we decided to place them directly behind the propellers, and this was for a number of reasons. The location of this exhaust sees advantages in the protection from foreign objects, which leads to an increased survivability rate. And also the takeoff and landing can be done on a range of terrains rather than just on a concrete runway. The exhaust system can be seen here to the right. Slide. The location of the power plant was also important, and we chose to use a tractor design and mount it onto the front of our fuselage. The main reason for this location was due to the fact that the air that would be coming into our power plant would be much cleaner if it was placed out of the way of any other hindrance. It provides great efficiency as well as great stability. Slide. The fuel system was one of the last things we had to consider. The bladder fuel tanks were chosen for our design, and mainly due to their great survivability through their self-sealing technology, which essentially means that if they're shot through, that they can heat themselves up and seal themselves and prevent leaks and fires. It allows for the storage of the fuel in the wing as well as the fuselage. It was calculated that we need to carry about 3,300 pounds of fuel, which means that we needed to put 61.4 cubic feet in the fuselage and 9.2 cubic feet in each wing. The fuel type that was chosen was the JP8, and this is because it was commonly used in military aircraft, and its density allows us to be lighter and complete our ferry missions as well as our payload missions. Slide.
Hello, I'm Jan Cosme, and I'll be talking to you about the landing gear for our aircraft. When deciding the type of landing gear we're going to use, first thing we needed to do was figure out the configuration. For an aircraft our size, there are really two main options: the tail dragger configuration or the tricycle configuration. The problem with the tail dragger, though, is that it's very unstable, but it was used in a lot of aircrafts in the past. So we chose the tricycle configuration because it's a whole lot more stable and versatile. Along with that, the tricycle configuration allows you to land on a runway that isn't perfectly aligned with the nose, whereas with other configurations, you have to be perfectly aligned with the runway to land. Another advantage of the tricycle configuration is that it allows for above average forward visibility of the ground or runway. Next was the location of the wheels. First, we needed to figure out where the center of gravity was for the aircraft itself, so we could load the wheels accordingly. Next was to calculate the overturn angle, which needed to be less than 63 degrees for stability reasons. And tip back angle was chose to be at the lowest it could be, between 15 and 25 degrees. We chose 15 degrees. So the tail back angle had to be at its lowest threshold as well, 10 degrees. Using the overturn angle, the Y locations of the main wheels were found, and the location of the nose wheel was at perfectly in line with the center of the fuselage. Next, please. Next was the tire sizing. Using the methods in our book and historical data, we found the nose tire to have a diameter, or calculated diameter, of 28.50 degrees and a width of 7.37 inches. And the main wheels to have 35.94 inches in width and 10.54 inches in width. Granted, these are calculations that these are the bare minimum that the tires need to be. After looking through the chart, the nose wheel was found to be a type 730 by 7.7 inch wheel, and the main wheels were chosen to be a type 736 by 11 inch wheel. Next, please. The next slide here is just the CAD drawings for the wheels themselves and the wheel and wheel hub assembly. Next, please. Next is tire pressure. These wheels will be filled up with dry nitrogen, just because historically and more recently aircrafts have used dry nitrogen to fill up their tires. But the tire pressure comes with certain limitations. Depending on the PSI rating, it's directly related as to what type of ground you can land on. For the nose tire, the minimum amount, or the minimum condition that you can land in, is hard packed sand to an aircraft carrier. For the main tires, you can land from a range of dry grass on hard soil to an aircraft carrier. Due to the limitation of the main tires, we have to just cut it at dry grass on hard soil. Next, please. Next is the shock absorbers. After doing some studies, we went with the oleo-pneumatic shock absorber configuration. The advantages of this configuration is that it's lightweight as compared to a spring system, which you would see in a car or basic vehicle. And it absorbs the kinetic energy experienced by the landing gear during the impact. Where the shock absorbers in a car does very well, but with the amount of force that you're coming down on a runway, it will not be good to have metal springs as your shock absorbers. After calculating using methods in the book, the stroke length was found to be 17.43 inches. The total oleo length was 52.29 inches, diameter 3.90 for the main wheels, and 2.66 inches for the nose wheel. This configuration leaves an excess of 29 inches to accommodate for any sort of foreseeable displacement of the propeller below the fuselage due to mounting configurations. This is really good because we needed at least, I believe, 8 inches of clearance to the ground, and we have much more than that. Next, please. Lastly was choosing the retraction system. It was very easy to know that we needed a retraction system on this aircraft, mainly because it provides protection for the landing gear and improves aerodynamic properties. When doing ferry missions or the design missions or any sort of mission for the military at all, you want to have the highest percentage of survivability as possible. And damage to the landing gear would be detrimental to the survivability rate of the aircraft or its crew. When choosing the retraction system, we chose a push-pull rod system. And we needed to figure out how it would be driven. We chose a hydraulic system just because manually driven systems would not be very efficient in this case. And any sort of electronic system would not work due to the fact that electronic motors cannot withstand repeated impulses associated with landings of an aircraft this type. Next, please.
So now we're going to be talking a little bit about the fuselage design as well as the crew station. Slide. This is the fuselage design. It can be seen here. We were designing our aircraft to be able to hold up to 2 crew members, which was a design requirement. And we also tried to design it to minimize as much wasted space as possible. We designed our fuselage to be 37.5 feet in length. And the streamlined profiles seen below help minimize radar detectability. Slide. The crew station. So for the crew station, we had to look at what type of seats we had to put in our aircraft. We chose the EAS4710 ejection system from Collins Aerospace. The dimensions in a picture can be seen here below, but the dimensions are 46 inches in height, 24 inches in width, 32 inches in depth. And we decided to add 18 inches overhead and 30 inches underneath for the legroom for the pilots to add for comfortability. Slide. This is the design of the overall crew station. It can be seen here that the 2 ejection seats are placed in there, and there are also there's also ample room for any panels, dials, or other equipment that you would need in the cockpit for a flight operation. Slide. This is the canopy that we chose to put over our cockpit and our crew station. It is long enough to fit over, and it is aerodynamic enough to allow for clean flight. Slide. So the next part is weapons and survivability. The weapons carriage. There were a lot of parameters that we had to consider when we were looking at which weapons we wanted to select. Flexibility, safety, drag, and stealth were just a few of them. Our design requirement was to carry a 3,300 pound payload, and we could choose from a range of rockets, missiles, and guns dispersed over 5 hardpoints, and we chose to have 2 under each wing and 1 hardpoint underneath the fuselage. Slide. So these are the missiles that we chose to select. The first missile we selected were 2 AIM-9L Sidewinder air-to-air missiles, which can be seen here to the right on the top. And we also chose 2 AGM-65 Maverick guided air-to-ground missiles, which can also be seen here to the right. For the guns, we chose 1 FN Herstal M3P machine gun, which is mounted underneath the fuselage. And we also chose 2 GAIT M20 A1 potted guns, which would be integrated to the wings. Slide. So for the weapon carriage and deployment selection, we chose for the Sidewinder, we chose the rail launch method, which can be seen here to the right. And for the Maverick, we chose the ejection method, and this was mainly due because it is much heavier than any of the other armament that we would be carrying. So the ejection method would be best suited for this type of armament. Slide. The placement of the weapons can be seen here in this CAD drawing. As I mentioned before, there are 5 hardpoints. There's 2 on each wings. The Sidewinders are on the tips of the wings, and the Mavericks are towards the center of the wings. It can also be noted where the landing gear positions are, as well as the fuel tanks, which we will see in the next slide. This is a picture of the wing and a layout of where the collapsible landing gear will be. You can see that here to the left, as well as the gun that was integrated in the middle and the fuel tank that was used, about 17-gallon bladder fuel tank. Slide. Some of the stealth features that were incorporated into our aircraft include the slender fuselage, which reduced on the radar detectability. The turboprop exhaust that we chose reduces infrared detectability as well. We also chose to paint our aircraft with a gray or blue paint on the underside in order to try to blend in with the sky, so that when enemies are viewing us from the ground, we would blend in a little bit better. Additionally, the turboprop engine that we chose creates a lot less noise than some of the other engine types. Therefore, we would be a lot quieter when we are conducting our missions. Slide. Vulnerability conditions are also very important. The equation that was used to calculate the vulnerable area can be seen here. It is the projected area times the probability of a given hit. And all of the important components can be seen here in the table below. Slide.
All right, my name is Tristan Kroger, and we'll be moving on to structures. So first and foremost, we're capable of analyzing boundary conditions on equivalent airspeed under various load factors, represented as N here, using a VN diagram. Directing our attention to the numbered curves on this diagram, we can observe the upper limit, curve 1, is initially defined as a quadratic function of airspeed defined in our textbook, and that's shown to the left. Then we construct a vertical boundary, curve 2, which occurs at the peak load factor in high alpha conditions, and a horizontal boundary layer, curve 3, which represents our high speed limit dive speed, which is taken to be around 50% greater than cruise speed. Observing the lower boundaries, we can see that curve 4 is also a quadratic function of airspeed derived from the same expression governing curve 1. And the lower limit is, of course, bounded by our cruise condition, and that is curve 5. Moving on to fuselage structure. Now, upon immediate observation of our fuselage, we note that the interior is comprised of a fairly traditional semi-monocoque structure. That is a structure composed of these cross-sectional load-bearing frames called bulkheads, linked lengthwise throughout the fuselage by the skin longerons and stringers. By removing many of the internal structural members, you would see in a truss frame this not only reduces weight and material costs, but also improves fuel economy, while retaining favorable survivability qualities and carrying capacity in comparison to like a regular monocoque structure, which would actually omit most of these internal linkage members. This is all comprised of aluminum, which we'll be touching on shortly. And there's an image of our fuselage, bulkheads, longerons, and stringers. On the wings, you can immediately observe that our wing is comprised of a fairly common configuration of aluminum ribs, spars, and stringers. It may be difficult to see, but we've also incorporated a proprietary skin of carbon fiber laminates and sandwiches, expected to possess material qualities similar to those of Thornell VMX-24. Naturally, similar structures have been incorporated in our horizontal and vertical tail components. Here's a dimension diagram of our internal structures. We see that the ribs conform to a tapered envelope beginning with an NACA 63-415 section at the root and terminating with the smaller 63-212 section around the tip. When identifying viable materials for these structures, we performed a qualitative analysis on various standard aerospace materials like steel, aluminum, and titanium, primarily with respect to machinability and compromises between material strength and density. This is usually accomplished using Ashby charts like the one shown on the left. For example, using a formula for simple cantilever beam deflection, which is common in tip displacement analysis, and expressing that equation in terms of length and volume, it becomes proportional to the ratio between density and the third root of elastic modulus, which would correspond to this length on the diagram right here, or that slope. Translating it to the left, we see that alloys of aluminum boast superior material qualities in terms of bin mass design for tip displacement compared to, say, titanium and steels. All right, moving on. All right, now we can observe some of our simulations with respect to structural integrity, constructing a wing box simplification in Abacus and running a simplified cantilever beam analysis, applying max load conditions to a single wing. We observe Mises stress values generally ranging between 0 and around 44.2 KSI, not exceeding yield conditions. Applying similar constraints and loading conditions to the interior structural components, omitting the skin stringers, etc. For one wing and running a tip displacement analysis in SolidWorks, we additionally see that tip deflection is not expected to exceed 8 inches, which is fairly standard for aircraft in this niche. All right, tail design systems and weight estimation. Moving on to tail components, we ultimately opted to incorporate a conventional tail arrangement, specifically because it happens to be among the lightest configurations available due to the omission of other bodies and the need for a wider fuselage. We had no special needs or concern with respect to the stability of the aircraft that would depend specifically on an unorthodox tail arrangement. But of special interest is the ability to retain at least a third of the total rudder area outside the wake of the horizontal tail. which ultimately contributes to spin recovery. And our design satisfies that criteria. With respect to geometric parameters, we first obtained horizontal and vertical volume coefficients of 0.7 and 0.06 respectively, which came from historical values for the jet trainer class. Additionally, the tail's moment arm, the distance between the quarter cord of the wing and its own quarter cord, is rated for the front mounted propeller configurations to comprise around 60% of the fuselage length. Again, from historical values in the textbook, we additionally obtained a taper ratio of 0.4 for both components, as well as aspect ratios of 3.5 and 1.2 for the horizontal and vertical tails respectively. In terms of control surfaces, we opted to use a notched balance configuration to maximize the available area, which comprises around 35% of the total airfoil area for both the vertical and horizontal components. As mentioned previously, the tail design incorporates aluminum structures comprised of ribs and spars in the same manner as the wing. All right, on to subsystem weight approximations. Using equations derived in the textbook, we were able to obtain generous weight estimates for an assortment of subsystems, which were ultimately accounted for by altering the density of our cruise station model to match the total weight of the cruise station and the subsystems. We found a subsystem weight for controls of 530 pounds, instruments comprised about 128 pounds, 632 pounds for avionics, 447 pounds for electrical, 38 pounds for cooling systems, 435 pounds for furnishings, and around 230 pounds for air conditioning and de-icing. After plugging these into our SolidWorks model, again, changing the density of the cruise station to encompass the total weight of all of our subsystems, we found an empty weight of approximately 8,754 pounds, subtracting fuel and, of course, weapon systems. And for our design mission, total loaded weight is around 12,742 pounds. We can additionally perform a center of gravity approximation using SolidWorks with the mass properties analysis, which returns a center of gravity located around 167.8 inches from the nose, perfectly aligned with the fuselage axis due to symmetry, and 15.8 inches above the chord plane of each wing.
Hello, my name is Samuel Beck, and I'll be going over stability. Slide. So stability analysis can be broken up into longitudinal stability and directional and lateral stability. Longitudinal stability concerns itself with the aircraft's pitching stability under steady level flight. So for pitching moment contributions, we have the wing, fuselage, horizontal tail, and engine. And on the right side of the slide, we have the stability axes and directions. X direction goes out the nose, Y direction goes out the right wing, and Z direction points vertically up. In our pitching moment versus alpha, we can see that our aircraft must generate moments that oppose a change in angle of attack. A change in angle of attack is essentially a wind disturbance or a wind gust caused by some perturbations. So as angle of attack increases, the nose will pitch up, and we have to counteract that nose pitching up with a negative pitching moment. So that will bring the nose back down. Slide. So in terms of our pitching moment arms, our wing pitching moment arms are relative to the aerodynamic center of the wings. And it's noted that the center of gravity is measured from a reference datum, which is the nose of our aircraft. The aerodynamic center is used with these equations in the book. It's noted that the aerodynamic center is at the quarter cord of the airfoil using thin airfoil theory. However, to approximate a better value in terms of Mach number and speed, we can use this delta AC. So our center of gravity of our entire aircraft with respect to that reference datum at the nose was 4.262 meters. And measured moment arms from datum, the distances from the center of gravity and the aerodynamic center of the wing, as well as the aerodynamic center of the horizontal tail, and the center of gravity of the engine housing are used to calculate the entire pitching moment contribution. Slide. So the derivative of pitching moment with respect to angle of attack must be negative for our aircraft to ensure longitudinal static stability. And the equation above gives our contributions from the fuselage, the wing, the horizontal tail, and the engine housing. It's noted that the CM alpha with respect to fuselage is a function of our fuselage width, length, and an empirical pitching moment factor for the fuselage. The FP alpha all the way on the right side of the CM alpha term is the inlet normal force of our propeller, and that's a function of our propeller design, including blades and area of blades. It turns out that our CM alpha was negative 0.376, and that ensures longitudinal static stability. And this table is all the variables we used in the equation on top. Slide. For neutral point and static margin, neutral point occurs when the derivative of the pitching moment is 0, and that will be used to calculate the static margin as a percentage distance of the mean aerodynamic chord. Slide. So our neutral point was calculated as 4.484 meters. And the static margin is the distance between the center of gravity and the neutral point, as stated before, as a percentage of the mean aerodynamic chord. And it's noted that a positive static margin yields a stable aircraft since the center of gravity is ahead of the neutral point. Slide. Lateral directional stability concerns itself with the roll and the yaw angles. A negative rolling moment derivative with respect to side slip angle is stabilizing, and that's where we get our dihedral effect. That's a stabilizing contribution to our aircraft. So it's noted that Cn beta has to be greater than 0 to ensure directional stability, and Cl beta has to be negative to ensure lateral directional stability. On the right side figure, you have a qualitative analysis on the rolling moment versus the side slip angle. So a positive rolling moment coefficient is essentially a right wing down moment, and a positive side slip angle is essentially a right wing down perturbation. So in the tables below, we have our yaw moment coefficient with respect to side slip is a positive value of 0.1, and our roll moment coefficient is a negative value with respect to side slip, and it was taken as negative 0.12. Slide. For our trim analysis, we decided to do static trim, and we needed our total pitching moment had to be 0 in steady level flight at an angle of attack of 0 degrees and a flap deflection of 0 degrees. And the equation below is how we calculated the coefficient with respect to the center of gravity. In this table, you can see at 0 degrees flap deflection and 0 degrees angle of attack, we get approximately a 0 total pitching moment at 0.0032. And at negative flap deflections of negative 2 degrees and 2 degrees, we have moment coefficient about the center of gravity at 0.02, which is a positive for a negative flap deflection, and a negative value at negative 0.01217 for a positive flap deflection. Slide.
Hi, I'm Daniel Singer, and I'll be talking about the performance of our aircraft. Slide. So for the range analysis, we calculated the range using the Burgett range equation. And what this equation does is it relates the velocity, the lift drag ratio, the weight, and the specific fuel consumption of our aircraft. And by relating these terms, we were able to find that with our internal fuel supply, that we have a maximum range of 748 nautical miles. And with external fuel tanks, we can get that range up to 1,447 nautical miles. So what this shows is that our target range for our design mission was about 200 nautical miles. So we far exceed that, even with just the internal fuel supply. And then the target range for the ferry mission was 900 nautical miles. So in order to be able to get that far, we'd have to use some sort of external fuel tank solution. But that mission does not require as large of a payload, so that is easily obtainable. Slide. So the endurance of our aircraft was calculated using the total endurance equation, also known as the instantaneous endurance. And this is very similar to the Breguet range equation, except that it does not use velocity as part of the calculation. So calculating it with just our internal fuel supply, we found that our maximum endurance would be 2.69 hours. And then with external fuel tanks, that we were able to get that up to 5.21 hours. So our target endurance for the loiter portion of the mission is about 4 hours. So we cannot quite get there on just internal fuel supply, but with an external fuel solution, we're able to exceed that endurance target. Slide. The next performance thing that we took a look at was the takeoff distance. And this was important because we needed to keep our takeoff distance under 4,000 feet with a 50-foot obstacle as per military standards. And so to find this, you would take the sum of 3 intermediary quantities: the ground roll distance, the transition to climb, and the climb. The ground roll is just the portion that the aircraft is accelerating up past the takeoff velocity, which is found as a function of the stall velocity. And then transition to climb is the horizontal distance it travels in order to reach a steady climb angle. And then the climb distance is however much further the aircraft needs to go in order to clear the obstacle and enter and I guess be off the ground by that point. Slide. So by using the approach angle, the stall velocity, and the height of the obstacle, we were able to calculate these 3 intermediary distances. We found that our ground roll would be about 670 feet. Our transition to climb would take 827 feet, and then our total climb would be 244 feet in order to clear the obstacle. So this would give us an estimated takeoff distance of 1,741 feet, which is well under our 4,000 feet constraint. And then, so the next we had to ensure that our landing distance as well would be able to fit within the same 4,000 feet, 50-foot obstacle constraints. And in order to find this, the approach distance is basically it's the amount of horizontal space we need to clear the obstacle on our approach angle. Then our flare distance would be about the equivalent of the transition distance from the takeoff. And this is just how far the aircraft needs to travel before it touches down on the ground. And then the final interval is the ground roll distance, which is the amount of distance it takes to decelerate our velocity to 0. Slide. So by using the approach angle and functions of the stall velocity and height of the obstacle, we were able to calculate these 3 distances. We found that our approach distance would be about 216 feet. Our flare distance would be 294 feet. And then our ground roll, which was the dominant factor, would be 1,722 feet, which leads to a total estimated landing distance of 2,232 feet, which is well within our 4,000 feet constraints. Slide. So a summary of this, these are just a summary of all the things that I just said for better clarity. Thank you.
Here's a quick cost analysis for you guys. Next slide, please. So just a quick overview here. The per unit cost of acquiring one of these A55 Vultures is around $21.7 million, with manufacturing taking over 2/3 of that. Raw materials, $4 million, quality control, $2 million, and engineering, $1.5 million. Next, please. As far as non-reoccurring costs goes, it's separated into 4 parts: engineering, tooling, quality control, and manufacturing. Engineering engineering, this aircraft costs about $9,601,124. Tooling, nearly 9.3 million. Quality control, 776 million, and manufacturing itself, $93.8 million. Next, please. The acquisition cost of 50 A55 Vulture aircrafts is nearly $21.7 million per unit, which for light aircraft or light trainer aircrafts or aircrafts of our suit, they range from 20 to 30 million. So we're at the bottom threshold here, which puts us at a competitive advantage when going after military or governmental contracts. To get the acquisition cost of 50 aircrafts, we need to add the developmental cost, support costs, flight test costs, manufacturing materials costs, engine production cost, avionics, RDTE, and flyaway, and divide it all by 50, and that gives you a value of nearly $21.7 million. Next is operating cost. Operating cost is separated into four main parts: fuel and oil cost. Those are joined together because oil only takes up about 1% of the total fuel cost. Maintenance cost, which is the material cost per flight and the material cost per flight hour. Tire replacement and brake replacement. Tires need to be replaced every 260 landings. And when we were designing our aircraft, we had 155 design missions, 148 ferry missions, and 140 training missions. That gives us a total of 450 landings, which puts us a little bit over 1.5 when divided by 260. And just to round up for safety reasons, I went with 2 replacements over the year, and that brought a total of $6,000 into the maintenance cost. Brake replacements need to be done every 18 to 36 months, and that costs about $25,000. In this case, I said that the brakes were replaced once during this year period, just because 1,200 hours is a lot of flight hours, even in the military realm. And maintenance cost. So when an aircraft of our type will incur not only the material cost, but the cost of having a maintenance crew, usually. But anything that has to do with the military, the cost of having a maintenance crew is equal to the cost of having the material cost. So that just wasn't calculated. And the 2-man crew cost and insurance is 2% of the total operating cost for the year. After calculating all of these, that gives us about a $1 million operational cost over the year, with the crew actually holding the most amount of weight in this cost. When divided by the amount of hours that we're flying, that gives us $844.91 an hour to fly this aircraft. When comparing to other similar aircrafts of our type, they usually range around $1,000 or a little bit more. So that puts us at a competitive advantage over our competitors. Next slide, please.
All right, so here are our references, and that would be the end of our presentation. We'd like to open up to any questions if we have time.
Thank you.
Otherwise, thanks for listening.
Thank you for your presentation. So it's about 15 minutes. So I think I had a class, a specific class talking about a presentation and everything. I spent a whole hour talking about it. So do you guys remember what are my requirements of the time for the presentation and Q&A?
Yes.
I believe it was 45 minutes and 15 minutes. Yes.
Yeah, I posted that video, so you can check back. It's 30 minutes presentation and 15 minutes Q&A. That's how I can make sure that the presentation can be finished at the on time, so I can go to the another one, because I'm having like 7 groups in a whole day, and right now you guys are having 50 minutes. And now I just text the group 7. I asked them to wait because I don't think I can be there on time. So it's 30 minutes presentation plus 15 minutes Q&A, and then I can have some time to go there to the next group to start their group presentation. So that is the first one. And second one is that, I don't know, so I have been start from 9 in the morning, and this is like I have one more group to go. I feel that I normally interact with the different group at the like 5 minutes before the presentation start, and they were like super happy and talk to each other, and they kind of, I can feel that they enjoy the whole not just the presentation, also the like, because they talk with me a lot, like office hour and everything as a group. That's kind of thing that I want to see for my students. I want them not just torture them, okay, you need to work hard on your mini report, and I give you a revise, and you need to revise that. I'm a picky person, that's true. I want to push you to work as hard as you can. But at the same time, I want you guys to enjoy the process and the cooperating with your group mates and everything. And the senior design is more like a like simulation of what you will see after you graduate. I believe most of you will graduate very soon. So you will work in a group, and we want to see that you are happily working with everyone in your group. You know what I mean?
Yes, ma'am.
Yeah.
So that is a very important thing. So in this class this semester, I didn't talk anything about leadership, team management, and anything, because, well, look at me. I have never been a leader in my whole life, so I don't think I'm capable of saying anything on that. In my previous semester, like in the aero design last semester, I was co-teaching with a NASA engineer. He was a retired NASA engineer, and he spent a whole semester talking about team management, leadership, and everything, how to make the whole team work happily together. I didn't mention anything about that this semester. It's not because it's not important. It's because I feel that I'm not capable of saying that, because I didn't have any experience as a team lead or anything. But at the same time, I do want you to like work happily together. That's also better for the result of your group, right? You enjoy the process, you have the better result. That's everybody want to see. But when I also, same as every group, I came 5 minutes early. What I see that you guys don't look happy. I don't know why. I said hi, no one responds. So this is second thing I want to talk about, and I hope that you can consider on that, like after this semester, or when you go to nursery, or when you go to graduate school, there are more group work you need to do. You probably need to think about how to have a better working environment with your group members. And as for the slides and everything, first, your presentation start from airfoil selection. And from a big picture, I want to say, we need some guidance on the wing design, right? It's not that, okay, now this is our design, this is the wing. As I put in the mini project, we start from, at the very beginning, we don't have everything, we didn't have anything designed, but we have the requirements. So we have the landing distance, takeoff distance, range, endurance, surface seating, payload, all the requirements. So we use that requirements to do a initial estimation, right? Remember, we have the initial weight estimation, we have the thrust weight ratio estimation, we have the wind loading estimation, lift drag ratio estimation, and then we use the requirements to have this estimation and use this initial estimation to guide our design. And then we start, okay, why we want to design wing in this way? Why we want to select this power plant? Why we want to design the tail in this way, right? But I feel that you guys skip that part. So you start from the wing design directly, and people will feel, okay, why you want to design wing this way, right?
Correct, yeah.
Yeah, it's hard to justify that. So for the airfoil selection, I personally feel that it's not just airfoil selection and also including the power plant and everything. I feel that you put too much time on the basic background knowledge. It's like you start from, okay, assumption and camber, airfoil camber, thickness, and why you don't want to choose 7 series, 16 series, 5 series, 4 series, 6 series, and then you start your selection. And I would say that for a presentation of your design, you start from your design directly. We don't want to see too much of the background information. We can read that from textbook, right? We want to see your design. That's why we have the same project for all 7 groups. We want to see what is your design. It's not the background information.
Yep.
Yeah. So I would consider that, well, to reduce the 15 minutes to 30 minutes, the first thing needs to go is the background information. We don't need to talk about the basic information of airfoil, why we don't want to choose all the different series, but we want to choose one. We skip all that part. And also for the power plant, why we don't want to choose turbofan, why we don't want to choose the piston engine. Start from your design directly. That's what we want to hear. Yes. So that is a very general feedback of the your presentation. And the next one is the airfoil selection continue. I don't, there's no page number, so can you change to the airfoil selection?
Yes, ma'am, we have 3 of those. I'll just scroll through them.
Yeah, there's a graph. There's a graph with the
drag puller?
yes, this one.
Yes.
So for the airfoil selection, yes, drag puller is very important. I agree, but we make a selection also based on the lift coefficient. I would like to see a lift coefficient versus angle tag. I would also want to see the drag coefficient, drag puller, and also lift to drag ratio, everything. So we make a selection based on everything. It's not just this single drag puller here. So yes, I know you have the lift coefficient versus angle tag later, but that is after you select your airfoil.
Oh, yes.
Yeah.
Yes.
So what I mean is that when you make decision that, okay, we have like, you gave like 9 options here, and there's only one graph of drag puller. I want to see, okay, what is the lift coefficient of this 9 airfoil performance of all these 9 airfoils, right? I want to see your plot of lift coefficient versus angle tag of this 9 airfoil on one graph. Then I can see, okay, this one indeed has the best lift coefficient versus angle tag, or for the same angle tag, this airfoil has the highest lift coefficient, or the highest angle tag for stalls when it stalls, right? So so that is like, we need to combine all these to make our decision. Okay, that's why we want to snap this airfoil. And also on this page, using the wind loading determined from the required takeoff land distance, and result target coefficient of lift is 0.748. Again, this value, I'm not sure if this is a calculation mistake or anything here. I feel this value is too low. For takeoff landing, we normally requires much higher coefficient. So we'll consider that takeoff and landing, the speed is lowest. So we want the lift coefficient to be the highest to generate enough lift to, let's say during takeoff, we need to lift off, right? So right now, 0.748, I don't think it's enough. So you need to double check your calculation to make sure this part is correct.
Mhm.
And for the wing geometry design, I think there are many items you said it's based on the history data. And what I want to see is that it's more based on the requirement. So it backs again, we want to put the requirement at the very beginning. What is the lift coefficient required? What is a lift drag ratio required at the very beginning? And then use that one as guidance for the wing geometry design instead of saying, okay, this is based on the history data. Okay, that one is also based on history data. If everything is designed based on history data, in the end, you will design an aircraft that is the average of the history data, right? So at the very beginning, of course, we didn't have anything. We can use the history data, but once we have the initial estimation, your design should be based on the requirement, the initial estimation. So what I want to see is that, okay, this design is because we want to satisfy this requirement. It's not just like everything based on the history data. So history data is, we can constrain that just at the very beginning. It's a very beginning stage of the design. So like at the beginning of semester, we didn't have anything yet. We can use the history data, but for this one, I think it's like too much. And for the next 3 slides, I think in the presentation, I heard you said that, okay, these are 3 graphs are pretty much the same, and that's it. So I was thinking if all this, I'm thinking when everything you put in the slides or you want to explain, there should be some goal. But if you just explain the way, okay, all 6 are pretty much the same. I mean, why do you want to put it here? Right.
Right.
We have a goal.
Yeah, I would agree.
Yeah, we have a goal. We present our design to the audience at the end of semester. We want to show the best. If you show 3 slides with 6 graphs and during the presentation you say, okay, these are pretty much the same. I didn't say anything about that. I mean, what's the point, right?
Yeah.
So this is this part. And for the engine, as I said, I think there are several slides you can just skip. And for the propeller design, diameter. So we have the
Further down.
Yeah. Yes, this page. Yes, we have the tip speed constraint. Of course, we want to make sure that the tip speed is lower than the critical Mach number of whatever airplane you choose. That is for sure. So this is just one constraint. And there is also another constraint that is the weight constraint and power constraint. Remember that? So if you really want to show why you choose diameter of 8 feet, I would suggest that you put both constraints here. So one side, one part is tip speed, one part is weight constraint, and then for the both calculation, we find whichever is lowest, right? And then that should be the diameter of our propeller. So you either do not provide any information why you choose 8 feet, or you provide the complete one.
Yeah, so I was pulling it up just now. I believe the reason why this might have been omitted in the presentation was because we performed an analysis taking into consideration the weight constraint. And of course, it's our bad for omitting this, but the weight constraint ended up not being the limiting factor, and the actual limiting factor was the tip speed based on our calculations.
Okay,
But
now,
we definitely should have considered and included all of that as well.
okay. So you mean you calculate based on the weight constraint, calculate based on the tip speed, and in the end, tip speed is like more critical situation. So you in the end, the result you're saying, right? I understand.
Yes, ma'am.
Yeah. So yes. So it's true, but it still be nicer if you have two. And then conclusion is that okay, the tip speed is more critical constraint, so we choose 8 feet based on this.
Oh, yes, I agree. It still belonged in the presentation.
And also for the thrust, so it's like a 2 page later.
There we go.
Thrust. So the forward flight thrust and the static flight thrust. I want to know what is the thrust requirement, and then I want to compare with your design and the requirement again. So that's your design, the 1500 and 2300 certified requirement. So what is the requirement of the thrust of your group?
Anyone work on that section?
Well, the thrust requirement is just enough in order to generate enough lift so you can take off. And we added estimated thrust to weight ratio of, I believe, 9.92. So in order to generate enough lift, to generate enough thrust, I believe we needed, let's see, our weight was around 12,000 pounds. So then our thrust was needed to be about 1,200 pounds force. So we were able to hit.
Let's correct a little bit anything first. Mix the thrust and the lift. Lift is lift. Lift is the contribution for the wing. Your wing is able to generate lift to lift your aircraft. Thrust is so like acceleration and everything. So so it'd be nicer if you can include here that the thrust requirement, like the thrust weight ratio. What was the thrust weight ratio you just said?
I believe the thrust to weight ratio, I'd have to pull up the specific number, but I believe it was
around 1.25.
Yeah, around 0.125. Yeah.
Yes. So it's very high. It's very high. You can check the reasonable range of the thrust weight ratio of our type of aircraft to see if it's in the reasonable range. And if it's in I might be wrong. If it's in the reasonable range, I would suggest that the thrust weight ratio times the takeoff weight, and you put here what is that is the thrust required, right? And then we have the required. We have the thrust generated by your aircraft, and we say, okay, our design satisfy the requirements, right?
Right. Yeah.
Yes, ma'am.
Like that.
Yeah. So that is that part, and also for the landing gear. Let me see. The CAD drawing, I don't think it's necessary here because as from the presentation, I don't think there's any description of the CAD drawing anyway. So yes, you probably can skip that. And also the fuselage design, you provide the length, and I would like to see what if you provide one dimension. I was curious, like what is the width? What is the finest ratio? If you want to provide something, provide a computer, right? That's what I feel. So for the fuselage design, if you want to really put some parameter here, like length, width, finest ratio, provide a complete one. And for the crew station design, I think the most important requirements they are the visibility, the angle, the elbow nose angle, the side angle, and back to the tail. So for the attack aircraft, the most important part is that we want to make sure that pilot has the visibility. So in addition to all this dimension and all the property, everything you give here, I would consider it's better if you can include the visibility features of your crew station here. So it's like, what is the over the nose angle, what is the side angle, and back to the tail, the angle back to the tail. So to make sure that it satisfies the visibility requirements. And the weapon carriage must be able to carry 3,300 pounds. So is that a typo or anything?
Yeah, I think that might have been a typo from the from fuel, because I did that as well.
Okay, I think it should be 3,000, right?
Yeah, because our fuel is at 3,300 at one point, and I think I might have mixed those up. So that's my bad. I apologize.
It's fine. It's fine. It's just a very small mistake. And the weapon selection, the guns, and there is a graph here. I was wondering what graph represents. It's kind of the next, yes, the last page.
Oh, the last page. So
the guns and the two, you put two different machine guns, pointed guns there, and yes, and there's a graph. There's a.
it's not a graph. This is apparently when whoever was pulling the CAD drawing, that would be the template where you would have like somebody's information about the drawing.
What is the drawing about?
It's like a.
Oh, that's just the gun
Sure.
that we just placed into the. It was just like for placeholding.
Okay.
Like,
thank you. For the VN diagram,
Yep. Here we go.
so the line 5 you put as the cruise speed.
Oh, sorry. It approaches the cruise speed, but trying to remember what I misspoke there. I was trying to.
Yeah. So
put my notes.
obviously it's not a cruise speed. It's
It isn't.
Yeah. So you probably need to correct that and make sure it's not. There's no similar thing in the final report. And for the
Correct. No, the final report is correct. That was my mistake.
okay, great.
Sorry.
Great. So for the wing structure,
Go.
yes, this one. So the picture on top, what is that? That is tail, right?
Oh yes, that was just kind of like I figured that I would try to save time by bringing the description of the tail structure into the same slide as the wings because the structures are familiar and the structures are similar. So I was trying to conserve time by knocking out both of them here.
I see. Sure. And then for the stress analysis,
This one right here.
yes, this one. So
Yes.
for I was a little curious. So this abacus screenshot, it shows that this line. I don't know how to visualize it. So what is this direction? Is the cross section of the
Okay, so or I guess in this direction would be the wingspan, and then like with the left side being the root and the right side being the tip. I
so
believe.
now you have the top and the bottom. What is that called? Spar cap? It's because let's say there's a box shape, and the box shape should be in way, right?
right?
Yeah, it should be kind of
Span
like,
direction. So let's say your abacus simulation should be IC from front, and then
Mhm.
it's hard for me to visualize like what kind of simulation I doing here. So why this is empty in the middle?
What? Wait, say that again. I'm sorry.
So for the wind box structure on top,
Yes.
it's a wind box structure. The cross section is box shape, right?
Yes. Yeah. Yeah. That's how it was modeled as a beam with a box cross section with the relevant dimensions of a box
Yes.
thickness.
Yeah, the cross section is a box shape, and then this box shape should be the same to from the wind root to the wind tip. So
Yeah.
I imagine that in the simulation, well, as you just described, what I see here is more like I see from front, and everything is from left to right is in the spanwise direction.
Yeah, left over right should be like the span of the wing. So the very
Yes.
right would be the tip and left is the root.
Mhm.
Yes.
Yes, and then why there's empty in the middle?
Why is there what empty in the middle?
Yeah.
Oh, I
Like I only see a top line and a bottom line. So what kind of structure are you simulating here? What is the cross section of the abacus simulation? What the cross section of the abacus simulation?
the cross section. What?
The cross section of abacus simulation.
I'm confused what you're asking, I guess.
So
There's a chance I may have perhaps modeled the beam incorrectly in abacus.
yeah. So now let's say this is fuselage, this is a wing, right?
Right.
And what I see from here, your abacus simulation should be like, okay, there's a lift, so it causes deflect upward, and
Mhm.
so the cross section of the wing should be box shape.
Right.
It is, yes, correct.
And then for your simulation here, abacus simulation, let's forget about everything else. For your simulation in abacus here, what is the cross section here? They say one line on top, one line on bottom. What's connected?
Oh, you know what? I think the mistake that I made was I think I modeled it originally as a box, like where it should have just been modeled as a straight line because it's already given the box profile in the beam characteristics. So I see what you're saying now.
Yeah, that's true.
Okay.
That's why I feel it's a little weird when I see a.
Yeah, I see now. Yeah. That'll have to be redone then, but
So it's better to correct that in the final report, and for the
okay.
So for the derivative of pitch moment with respect to angle of attack.
Pitch moment with respect to angle of attack.
That'd be the longitudinal, right?
That's longitudinal.
Yeah,
Yeah, it should be
should be before this.
right here. Or is it?
Yeah, right here. Right.
Or
Down one.
There's no page number, so let me check.
That's that one.
Yeah. I think any page is fine. So yeah, yes, this one. So let's say this one. So the X bar. So what does the X bar represent? So it's like the X bar, CG X bar. So we have a lot of X bar here.
So X bar CG is the distance from the nose to the center of gravity of the entire aircraft.
You may need to double check on that because XCG means the distance the actual distance from the nodes. Let's say if you choose nodes as datum, it's a distance from datum to the center of gravity. That is xCG. But when we put a bar there, it is the distance divided by the mean aerodynamic chord,
Mhm.
right? So you can check textbook on that. So that is like notation we use for the whole design. So you don't want to confuse on that. And when we talk about the X bar, it's a ratio. It's an actual distance over the mean aerodynamic chord. There should be no unit for this one, right?
It's normalized, yes.
Yeah.
So also you can check based on this equation. So the Cm alpha equal to Cl alpha times X bar minus X bar. So the X bar minus X bar should not have any units, because and then the Cm alpha equal to Cl alpha, the units can be consistent. You know what I mean?
Yep.
Yeah.
So be careful. The unit is not meter. It's not the actual distance. It's actually just a ratio, right?
Mhm.
So yes, and also you want to, and also I think that these several slides have the same problem, so you can check on that on the final report. And
Yeah,
for
so we'll have to go back and double check that. Yeah.
yes, and also for the trim analysis.
Yeah, we saw the report 9 correct, or report 8 corrections. We did it, I believe James did it versus flap deflection instead of for takeoff, cruise,
So
and landing, which we will have to correct that.
yeah, so just want to remind you that correct that in the final report. And also for the performance analysis, the range and endurance and everything, you have the internal fuel supply with external fuel tanks. So is your design include this with external fuel tanks or not?
What do you mean, like as if like mocked them up like in the CAD, or
No,
or
you
not?
actually design. I mean, your actual design when you design the fuel tank. So you have the both internal fuel tank and external fuel tank, or you only have the internal fuel tank?
Well,
We have an internal fuel tank. The external fuel tank is just auxiliary fuel tank we will load underneath the wing instead of a weapon.
yeah, so like there's so much pounds that we can carry in payload, so the external fuel tank would take the place of part of that payload, and it would be loaded under the wing instead of one of, say, the Sidewinder missiles or something.
So here is what I want to say. The place that you put the payload, let's say weapon, you cannot just simply put a fuel tank there, because fuel tank is not just a simple fuel tank. There are fuel tank feed systems. You need to consider how to put the fuel tank, fuel in the fuel tank to get into the engine, to make it really used by the engine. It's not simply, okay, this is just a location, I can put a weapon here, and when I don't put a weapon, I can put the fuel tank here. Then how can the fuel in the fuel tank can actually get into the engine and to be used by the engine?
Yeah, we would have to run an extra fuel line, I suppose.
There's a very complicated fuel feed system. So it's not that easy just to replace the location for the weapons and fuel tank.
I see.
So for the internal fuels, we actually do have the fuel tanks on the wings as well. So the fuel line already does run from the wings into the engine. It would just be an extra extra tubing to connect it to one of the hard points from where the wing the wing fuel tanks are.
So it's different. So the fuel tank connecting part is different from the weapons connecting point, right? It's separate, or do you use as the same place and interchangeable?
Well, it'd be the same location, but it would have to be a different connector, because it would have to have a tubing inside of it in order for the fuel to run into the wing directly.
Yeah, so make sure that if you really have the external fuel tank, it should be a different connecting point. with the weapons. Weapons has its own weapons connecting mechanism, how to eject your weapons and everything. And fuel tank should has its own mechanism, how to feed the fuel feed system to actually pour the fuel into the engine, right? So
Right.
they're not the same point. They're not interchangeable. And I think that's it. I would say overall good job. And again, I do want you guys to enjoy the whole semester and for the rest of the semester. That's it. Congratulations, you're done.
Thank you, Professor.
Thank you.
All right. Thank you so much, Ting. Sorry again for going
Thank
over
you.
time, but we appreciate you staying back to give us all of this feedback. We really appreciate it.
Yes,
Yeah,
we do.
thank you so much.
Much
Thank you,
appreciated.
Ting.
You have a great one.
Hey, good rest. I'm gonna go to the group 7 now.
Good.
Have a great day.
Thanks so much.
Have a good day.
Okay.